Larger picture of our universe, Earth's story is only a fleeting whisper. However, what deeper secrets do these whispers hold? Embark on a journey of discovery that delves deep into the enigma of our planet's weather. From the mystical forces of El Niño to the ancient rhythms of the Milankovitch cycle, we uncover the complex stories that nature itself has created. Consider this: when traveling across climate and time zones, could the elements that shape our world also reflect the grand design of the universe? This documentary invites you to explore these mysteries, promising a journey that spans the seen and the unseen, the known and the unknown. It is not just a quest for knowledge, but an odyssey that seeks to connect the essence of our existence with the mysteries of space and time. Imagine a world where the oceans are covered in ice. Here the glaciers stretch as far as the eye can see, and even the equator, a region synonymous with warmth and sunshine, is a barren, frozen desert. This is not a science fiction novel. This is Earth, but not as you know it. Welcome to the mystery of an ice-covered planet that scientists are still trying to solve. A few cold winters may seem unbearable. But what if winter lasts 100 million years? This question not only boggles the mind, but also challenges our understanding of the Earth's climate system. How can a planet teeming with life suddenly turn into a frozen ball? And more importantly, how did he get out of this icy prison? These questions have puzzled scientists for decades, and the answers are as complex as they are interesting. So, buckle up as we embark on a blood-curdling expedition to discover how Earth was frozen for an unimaginable 100 million years. Our planet has been traveling through space for 4.5 billion years, and its climate has not been static during this long journey. From the scorching heat of the Hayden Eon to the verdant landscapes of the Mesozoic era, the Earth has worn many climate suits. Each era tells a unique story, a chapter in the history of Earth's ever-changing climate. The Cambrian period, for example, was a time of warm tropical seas, while the Permian period saw a world struggling with extensive glaciation. You may be wondering, are these climate changes part of a natural cycle? To some extent, yes. The Earth oscillated between ice ages and warm periods called interglacials. These cycles are influenced by many factors, from solar radiation to ocean currents. But here's what's interesting. These natural cycles do not fully explain the extremes of the 100 million year freeze. This anomaly, a deviation from the norm, requires a deeper investigation. Imagine the equator, normally teeming with warmth and biodiversity, turned into a frozen wasteland. This isn't just another ice age, it's a freeze of epic proportions, a climate event so severe that it challenges our understanding of Earth's natural systems. When it comes to unlocking the secrets of Earth's ice, rocks are like the pages of a history book, each layer telling the story of past climates. One compelling piece of information is the rocks that were washed away by ice and dumped in ancient seas. These falling rocks can be found in unexpected places, like the center of today's great deserts. Their presence indicates a geological whisper, when ice covers even the most unexpected places. Ice cores are another valuable piece of the puzzle. These cores, extracted from the polar ice caps, contain tiny air bubbles, each of which captures a snapshot of the atmosphere at a different time. By analyzing these ancient air pockets, scientists can reconstruct past levels of carbon dioxide, methane, and other gases. The data paint a grim picture of sharp declines in greenhouse gas emissions during the Great Cold. Fossils provide another window into this frozen past. Even under the harshest conditions, life found a way to survive. Microbial fossils tell us that simple life forms existed and thrived during these long freezes. These resistant organisms can survive near underwater thermal springs or other warm microenvironments. Their existence shows the resilience of life, even as the Earth seems to be plunged into an endless winter. Rockfalls, ice cores, fossils. Each piece of evidence adds a new level of understanding to the complex governance of Earth's climate history. So what could cause such a long freeze? How did Earth, a planet teeming with life, survive the icy ordeal? One of the main theories that could explain this long freeze has to do with Earth's orbital patterns known as Milankovitch cycles. These cycles describe how the Earth's position and orientation in space changes over time, and how much sunlight affects the planet. Although these orbital shifts are associated with the short ice age, they cannot explain the 100 million year-long freeze. The cycles are not long enough to explain such a long cold. Another theory points to volcanic activity as a potential catalyst for cooling. Violent eruptions can send ash and gases into the atmosphere, blocking sunlight and causing temperatures to drop. However, the cooling effect of volcanic eruptions is usually short-lived, ranging from a few years to decades. Only volcanoes can plunge the Earth into a 100 million-year winter. The carbon cycle is another contender on the list of theories. This complex system regulates atmospheric carbon dioxide levels, a key factor in Earth's climate. Disruption of this cycle could theoretically lead to a drop in carbon dioxide levels, leading to deep freezes. But the question is, can such a collapse last for 100 million years? Although each of these theories describes a piece of the puzzle, none can explain the mystery of the 100 million-year freeze. A combination of factors may have contributed to this extraordinary event. So what if Milankovitch cycles, volcanic activity, and the carbon cycle can't fully explain this glacial mystery? His boldness stands out among the theories that attempt to explain the Earth's long freeze, the snowball Earth hypothesis. This theory asserts that the Earth is not only partially covered with ice, but completely covered from pole to pole. In this dire scenario, even the oceans would freeze, at least. Imagine a world where the seas were hard and the skies were cloudless, because even the moisture in the atmosphere would freeze. The snowshoe route includes a U-turn. This is an enhanced circular effect. As ice expands at the surface, it reflects more sunlight into space, further cooling the planet and causing more ice to form. This feedback loop can be caused by a variety of factors, including the reduction of greenhouse gases, the reduction of solar radiation, and even the configuration of continents affecting ocean currents. The snowflake Earth hypothesis is not without its critics. Some scientists argue that a complete freeze would have made life impossible, contradicting the fossil record, which suggests that life continued throughout this period. Proponents counter that submarine water can survive near thermal vents or in pockets of liquid water within the Earth's crust. The debate continues, and new information is constantly changing our understanding of this icy mystery. The snowball Earth hypothesis explains our climate, its currents, and the sustainability of life. Whether you find it compelling or controversial, it offers a fascinating prism through which to explore the mysteries of Earth's climactic past. One would expect life to cease on a world covered in ice. However, fossils tell a different story. Microorganisms seem to have survived this extreme climactic event. These microscopic life forms may have taken refuge in the deep sea, near hydrothermal vents, or even in the Earth's crust. Extreme conditions often play an important role in evolution, and the Great Freeze was no exception. Adaptation or extinction may have led to the emergence of new life forms, some of which may have been the ancestors of species living on Earth today. Fossils from this period show an amazing diversity of life, and cold temperatures may have catalyzed evolutionary innovation. What was life like in the frozen world? One theory suggests that hydrothermal vents on the ocean floor serve as heat sinks. These underwater oases can provide a stable environment, rich in nutrients, and sustain life. Other possibilities include subterranean lakes and even warm spots in the Earth's crust, suggesting that microenergy could be life's last refuge, a place of hope in a frigid world. Microbial resilience, evolutionary pressures, and potential escapees that allow life to survive contribute to the story of Earth's survival against all odds during 100 million years of permafrost. After 100 million years of ice, the Earth is finally melting. But how did the planet transform from a frozen realm into a world teeming with life? The mechanisms of this great melting are as interesting as the freezing itself. One theory is that the buildup of greenhouse gases, possibly from volcanic activity, may have started the warming process. As these gases accumulate, they trap heat, slowly raising the planet's temperature. Ocean currents may have played an important role in the distribution of heat. As the ice began to melt, currents accelerated the melting and carried warmer water from the equator to the poles. Reactivation of ocean currents would restore a dynamic climate system without dissipating heat, further destabilizing the ice regime. Another factor contributing to melting is increased solar radiation. Our sun is not a fixed star. Its orientation changes with time. Periods of increased solar activity can provide the scales with the extra energy they need to warm up. Even a small increase in solar energy that raises the Earth's average temperature by a few degrees can change the climate. This subtle shift can act in synergy with the Milankovitch cycle's natural variations in Earth's orbit, amplifying their effects and contributing to the destabilization of the frozen state. As the ice melts, the Earth's albedo, or Earth's reflectivity, will decrease, allowing the planet to absorb more heat and speed up melting. The massive melt is likely the result of several factors working together, including greenhouse gas emissions, reactivation of ocean currents, and our ever-changing solar exposure. And together, these elements rewrote Earth's history, turning the page from a frozen past to a future full of possibility. The 100 million year history of the Earth's freezing and subsequent thawing is not only a journey into the past, it holds lessons for the present and the future. Today, as we grapple with climate change, understanding these extreme historical events can provide valuable information. Today's climate change, largely due to human activity, makes the study of Earth's climate history more relevant than ever. Mechanisms that once caused natural melting may now be artificially accelerated by anthropogenic emissions of greenhouse gases. Melting glaciers, rising sea levels, and increasing wildfires are reminders of our planet's changing climate. We are not headed for the snowflake land that serves as a warning sign of modern extremism. The speed at which these changes occurred is unprecedented in human history, and they mirror the rapid shifts that ended the Great Freeze. Advances in technology provide us with tools to study Earth's climate. Satellites and space probes give us a spatial perspective that allows us to observe changes in real time. However, these same technological advances drive consumption and pollution, exacerbating today's climate problems. The story of Earth's 100 million year freeze serves as both a cautionary tale and a source of inspiration. By studying the mechanisms that lead to mass melting, we can better understand the levers that control the current climate system. This education is not just academic. It is an important tool for shaping a sustainable future. When thinking about Earth's climactic past, it's important to step back and consider our planet in a broader cosmic context. Earth is a tiny dot in the vastness of the universe, and yet its climate changes are a unique model in planetary science. Understanding Earth's climate extremes not only informs us about our planet, but also about the climatic conditions that may exist on other celestial bodies. In recent years, the study of exoplanets, planets orbiting stars outside the solar system, has increased dramatically. Some of these distant worlds have climates that are harsher than anything we've seen in Earth's history. By studying these exotic climates, we can improve our models and theories and gain a more complete understanding of what makes a planet habitable or uninhabitable. Well, we have released a video with an example of a detailed look at such models. The main goal of planetology is to find an Earth-like planet called 2.0 Earth. Such a discovery would not only change our understanding of the planet's formation and climate, but it would also have profound meaning in the search for an extraterrestrial life. The climate of this hypothetical twin will be of great interest. Could it also experience Earth-like climatic events? So, what does this tell us about the sustainability of life in the universe? The story of the Earth's 100 million years of freezing is a complex mystery that scientists are working on. From early theories about the structure of Earth's orbit to the hypothesis of a snowy Earth, each idea adds complexity to our understanding of this extreme climate phenomenon. Although no single theory can fully explain this long freeze, the interplay of many factors, including orbital changes, volcanic activity, and even cosmic impacts, offer a multifaceted view of Earth's climatic past. The wonder and mystery of Earth's climate is not limited to the past. They are closely related to our present and future. The sustainability of life, the mechanisms of dissolution, and the lessons of today's climate problems all form a parable that is instructive. About 20,000 years ago, our Earth was like an icy desert, where life was very difficult. This stage in our planet's history is known as the Ice Age. Even though we thought the Ice Age was over, we are now rapidly moving towards it. In less than 100,000 years, the Earth will once again become a lifeless sheet of ice. The reason for this is the Milankovitch cycle, which gradually changes the Earth's orbital position. The endless flow of these cycles dramatically alters the planet's climate over thousands of years. Be prepared. Today you will learn how the Ice Age began, why it was important to life on the planet, and how humans delayed its onset. The impact of Earth's orbital characteristics on climate change was first studied in detail by the Serbian geophysicist and mathematician Milutin Milankovitch. Studying the works of climatologists of that time, the young mathematician turned his attention to a very mysterious stage in the history of the Earth, the Ice Age. It was known that the planet's tilt angle and orbital length affected the temperature of the Earth, but none of the theories described at the time could explain the global winter. In 1911, Milankovitch began his landmark work on the Pleistocene glaciation chart, which ended about 11,500 years ago. During this period, the continents became covered with ice, and the global climate became warmer in just a short period of time. In addition to mathematical analysis, Milankovitch also made geological observations, studying ice cores, fossils, and sediments on the ocean floor to determine the type of climate at the time by measuring the ratio of oxygen to hydrogen. After many years of painstaking theoretical work, mathematicians concluded that the Earth's orbit changed in 3 cycles of different lengths over a period of 650,000 years. During the initial skepticism, geologists confirmed his theory, and after his death, there was a renewed interest in his work. The amount of sunlight that reaches the upper atmosphere is determined by 3 astrophysical properties of the planet: the inclination of the axis, the shape of the orbit, or the eccentricity of the axis precision. They are the basis for Milankovitch cycles. But first things first. Axial inclination is the angle of rotation of the axis as the planet moves around the Sun. It is responsible for the changing of the seasons on Earth. At present, the angle of inclination to the Sun is 23.5 degrees. it was 22.1 to 24 million years ago, 5 degrees, which is one of the main factors of global climate. The greater the angle of inclination of the axis, the more sunlight each hemisphere receives in summer and less in winter. This means that less ice flows mean cooler summers, warmer winters, and more ice cover. The inclination of the axis changes every 40,000 years, and we are currently in the middle of this cycle. According to NASA, melting will subside in about 9,800 years. Milankovitch believes that the most important factor in the Ice Age. Therefore, the entire length of the Milankovitch cycle depends on it. The next factor in climate change is eccentricity, deviation of an orbit from a perfect circle. Earth's orbit is not perfect. Under the influence of the gravitational attraction between the planets and the stars, the orbits of the planets are elongated into an elliptical shape. That is, the Earth does not receive the same solar heating for all hemispheres. Thus, in an elliptical orbit, the distance between a planet and a star varies depending on the path of the planet. Therefore, at the point closest to the Sun, perihelion, the Earth moves faster and receives more solar energy. And at the farthest point, aphelion, it moves more slowly with less heat. But so far, it hasn't had much of an impact on our climate, considering the very small eccentricity. But in about 100,000 years, according to the cycle theory, the shape of the orbit will become elliptical. This means that the Earth will receive 23% more sunlight at perihelion and less at aphelion, leading to very hot summers and cold winters. A final orbital feature is the Earth's rotation, or precession, on its axis. This wobble is caused by the gravitational pull of the Moon and Sun, which slowly changes the direction of the axis, resembling a slowly spinning top. One cycle of axial compression is less than 26,000 years. If that axis now points north, and we see the North Star, in thousands of years, people will see another star in its place, such as Kochab and other stars. The pressure cycle also makes conditions in one hemisphere more extreme than the other. In 13,000 years, NASA estimates that solar radiation will be stronger in the northern hemisphere, while the southern hemisphere will experience moderate seasonal variations. In addition to the planet's axis, the orbit can also change due to interactions with Jupiter and Saturn. As a result, the perihelion gradually moves away. Its rotation cycle lasts 112,000 years. Apsidal and axial compression can be considered a single process, so they both play an important role in determining climate changes and the timing of ice ages. Thus, the amount of sunlight and energy the Earth receives from the Sun depends on the cyclicity of our planet's 3 orbital characteristics. It should be noted that the Milankovitch cycles describe long-term changes of tens of thousands of years, but they cannot explain the climate changes of the last hundreds of years and the present. With a certain inclination, eccentricity, and precession cycle, the Earth's climate can expect serious and irreversible long-term changes. Thus, according to Milankovitch, 41 Earths could face a new ice age after 41,000 years. Ice ages are also cyclical. Although we cannot feel the direct effects of Milankovitch cycles, they affect the Earth's climate very slowly and gradually, so they have a very small effect on the temperature right now. Thus, after long-term changes, as the eccentricity increases, the inclination angle decreases, and the perihelion moves away from the Sun. The planet's surface is slowly receiving energy from the star, and the Earth is experiencing severe cooling. Over time, the amount of ice in the polar regions will increase. The concentration of ice will act as a reflector for sunlight reaching the surface, so the global temperature will start to drop further. Combined with other factors such as a decrease in the concentration of greenhouse gases in the atmosphere, or changes in ocean currents due to salinity and the position of the continents, an ice age begins that can last tens of millions of years. During this time, the Earth can change dramatically. Persistently cold winters will have a major impact on ocean water levels and precipitation in general. This will pose a significant threat to many non-adapted species, including humans. The impact on global infrastructure and economies would also be significant. Freezing temperatures can destroy power lines and roads, disrupting global trade and forcing people to seek safer places, prompting mass migration. As one cycle ends, another begins, leading to warming and the gradual end of the Ice Age. Ice melts, change the landscape, ocean levels rise, and temperatures return to moderate levels. We are now in the midst of an intergenerational period. The last glaciation occurred tens of thousands of years ago. So every 41,000 years, the Earth goes through an ice age. But this has changed in the last century. Humanity now has at least 100,000 years to prepare for global cooling. But that's not really good news. As far as we know, Milankovitch cycles do not strongly influence the current climate. They cannot be blamed for the current warming. Over the past 150 years, orbital cycles have not changed the amount of sunlight reaching Earth's surface. But on the contrary, the level of solar radiation has decreased in the last 50 years. In particular, not only the lower layers of the atmosphere, but also the upper layers, such as the stratosphere, should have been heated by solar energy, but instead cooled. Besides cycles, there are many other factors contributing to warming. The most important is the release of carbon dioxide into the atmosphere, which inhibits the release of heat from the atmosphere. Since 1970, global annual emissions have increased by nearly 90%, and global temperatures have risen by 34 degrees Celsius. In 2022, global CO2 emissions due to human activity will reach a record 37 gigatons. As early as 2030, temperatures may rise to another level. Given that the Earth is in an interglacial period, it should be cooling by now according to the Milankovitch cycles, but instead, the Ice Age cycle is increasing. Despite the delay of the Ice Age, it still has a serious impact on the entire planet, including its life as a result of the cycles. Changes in climate and environment always affect the evolution of biological species because they need to adapt to survive. Glacial cycles generally create different conditions for life, forcing species to first adapt to lower temperatures and then to move to a more favorable one. For example, during the last Ice Age in northeastern Australia, the composition of forests changed completely from tropical to dry sclerophyll forests, dominated by eucalypts. Thus, these forests were able to adapt to the continent's frequent dry spells. In general, all regions close to ice sheets and glaciers experienced some changes in vegetation. Some species of shrubs and trees in the American Southwest grew at lower elevations than they do now. Trees that did not exist 18,000 years ago appeared in the eastern United States. Another reason for the evolution of many species is the forced migration of various animals and insects. The harsh conditions in the northern regions forced many species of beet to change their habitat from North America and South Britain, some of which can now be found in Africa and India. However, at the same time, many species of beet became extinct due to difficulties in adaptation and natural selection pressure. On the other hand, migration of a species to different regions can lead to diversification. One famous example is the Galapagos, or Darwin's nest, birds of the same species that have different beak shapes due to their diet at different migration sites. Milankovitch cycles operate on timescales much longer than the lifespan of a single organism, but shorter than the lifespan of an entire species. These evolutionary changes have serious implications for accumulation and overall survival. As the climate changes, biological species must adapt to it, but one individual cannot pass on the skills to the next generation without surviving through the entire Milankovitch cycle. Therefore, the next thousands of generations will live in different conditions and will have new survival mechanisms that can be combined in future generations. Thus, Milankovitch cycles help species adapt to future changes. Also, orbital cycles affect human evolution. Climate change plays an important role in natural selection, which ensures that only the most adapted species survive and thrive. Thus, according to Elizabeth Verba's reverse impulse hypothesis, the transition from warm, moist conditions to cold, dry conditions led to the formation of the homogeneity that we have today. In particular, according to paleontologist Peter Monacle's study of the African coast, orbital changes coincided with other important stages of human evolution, such as the diversification of the Homo species and the expansion of the range of Homo erectus. That is, the Milankovitch cycle could be the impetus for the birth of all mankind. However, these ideas are in the active field of scientific research, but it is certain that climate change could have had a certain effect on the evolution of human ancestors, as it has happened to many representatives of the flora and fauna. That is why Milankovitch cycles are of great interest for studying the past and future of our planet. Scientists continue to investigate the impact of these cycles on reconstructing the full picture of Earth's evolution. In 2013, a team of Chinese scientists with lead author Hua Chunwu found new evidence for Milankovitch cycles in southern China's Mishan and Shanxi regions, which are the last Permian sedimentary environments. The Permian period began 298 million years ago and ended 252 million years ago, indicating the length of the orbital cycle. By comparing the periodicity of the magnetic data to pinpoint the cycles, paleontologists found evidence of a 405,000-year cycle in both areas, allowing them to trace the orbital cycle of the entire Paleozoic era. In addition, they discovered that the 34,000-year cycle of inclination may be influenced by Mars. In particular, Milankovitch cycles are important for studying not only the geological evolution of the Earth, but also other objects in the solar system. In 2022, Margaret L., a team of researchers led by Lanting, was able to reconstruct the frequency of Earth pressure to understand the history of the Earth-Moon system. Thanks for the loops written in 2. The 46-billion-year-old Joffrey Falls sediments were able to get a rough idea of the Moon's distance from Earth. The research team still needs data from the Precambrian period to accurately determine the evolutionary history of Earth's satellites, but the data has expanded what is known about the Moon's trajectory. Further modeling will be able to more accurately plot the trajectory of the satellite in the past and, especially, in the future. Milankovitch cycles play an important role in the Earth's climate pattern and the evolution of many biological organisms. Ice ages are inevitable for the planet due to cycles of melting, eccentricity, and decompression. In about 100,000 years, the Earth's northern hemisphere, or even the entire planet, may be covered by ice sheets again, and humans will have to adapt to the new conditions and grow along with the Earth. The concept of entropy, a measure of disorder and randomness in a system, plays an important role in predicting the end of the world. According to the second law of thermodynamics, in closed systems, entropy increases with time until it reaches a maximum. This basic principle of physics states that the universe can be viewed as a closed system moving toward a state of maximum entropy. This increase in entropy is often associated with the end of the world, leading to a phenomenon known as the triumph of entropy. In a world of high entropy, all energy distributions would be equal, and temperature differences would disappear. Homogeneity means that no work can be extracted from any part of the universe, since work depends on moving energy from areas of high concentration to low concentration. In such a state, all energy-consuming processes such as life, star shining, planet formation, or even black hole evaporation will cease. The universe will reach a state known as thermal equilibrium, where all points in space will have the same temperature and no more changes will occur. Visualizing a universe dominated by entropy evokes a picture of cosmic immobility and monotony. The bright space we see today, with its galaxies, stars, and planets, would be replaced by featureless space. Stars would run out of nuclear fuel, galaxies would no longer form, and black holes, the last bastions of gravitational order, would vaporize as a result of Hawking radiation. All that would remain would be a dilute soup of particles and radiation scattered over ever-expanding space, with no gradients to drive motion or form structures. As the universe moves inexorably toward its finale, the last black holes stand as monuments to earlier and more turbulent eras of the cosmos. These gravitational giants, remnants of decayed stars and engines at the centers of galaxies, would undergo a slow but inevitable transformation that would have profound implications for the ultimate purpose of the universe. The key to understanding their fate lies in a process known as Hawking radiation, a theoretical prediction by physicist Stephen Hawking that black holes are not completely black, but emit radiation due to quantum effects near their event horizons. Hawking radiation results from the creation of particle-antiparticle pairs in the vacuum near the event horizon of a black hole. From time to time, one particle falls into the black hole and another flies out, causing the black hole to lose mass over time. For large black holes, this process is extremely slow. It takes many orders of magnitude longer than the current age of the universe to have a noticeable effect. However, as the universe ages and expands, these last black holes will become protagonists on the cosmic stage, gradually vaporizing their mass in the form of Hawking radiation. The evaporation of the last black holes marks an important milestone on the universe's path toward maximum entropy and thermal equilibrium. By emitting Hawking radiation, they not only lose mass, but also eject energy back into the universe. However, this energy will be distributed in the increasingly rarefied space, contributing to an overall cooling and erosion of the energy density in space. When the last black hole evaporates, a process that could take up to 10 near-flexible 100 years, a time frame beyond human comprehension, there will be no significant concentrations of mass and energy left in the universe capable of forming new celestial bodies or driving cosmic phenomena. The significance of the evaporation of the last black hole goes beyond their role as cosmic reference points. It symbolizes the transition of the universe to a state in which no large-scale structures exist, and all that remains are low-energy photons, electrons, neutrinos, and possibly dark matter particles scattered throughout an ever-expanding space. This state represents the ultimate embodiment of entropy's triumph, a universe in which all available energy is used up and no work can be done. In the distant future, as the universe ages and evolves toward a state of maximum entropy, conditions for life as we know it will become increasingly difficult. Theoretical assumptions about survival in a degenerate universe, where stars have gone out and black holes have evaporated, paint a picture of extreme adaptation and ingenuity. If any forms of life or consciousness can survive in this distant future, they will have to adapt to the harsh conditions of a dying universe in ways that push the limits of our current understanding of biology, physics, and engineering. In such a universe, traditional sources of energy, such as sunlight or chemical reactions, would be scarce or non-existent. One possible survival strategy involves utilizing the most fundamental and common sources of energy. For example, Civilizations will be able to harness the Hawking radiation energy emitted by evaporating black holes, although this will require technological advances far beyond anything currently imaginable. Another speculative strategy might involve the direct conversion of mass to energy. As matter becomes increasingly dilute in an expanding universe, extracting useful energy from rare particles and radiation may be a way to sustain life. Advanced forms of matter manipulation or even energy extraction mechanisms at the quantum level that allow direct harnessing of the energy of subatomic particles could be utilized. Survival in a degenerate universe may also require radical changes in life forms themselves, perhaps through bioengineering or the development of post-biological life. Life could take the form of highly efficient, low-energy beings capable of functioning in an environment with minimal resources. These beings could be engineered to hibernate for long periods, awakening only when energy conditions are favorable, or to exist in a state of reduced metabolic activity, extending their lifespan to eons. Furthermore, given the isolation caused by the vast distances between the remaining energy sources, any surviving creatures should probably be highly autonomous, able to repair, reproduce, and evolve without outside interference. This could lead to forms of life or consciousness that are fundamentally different from anything we know, potentially based on entirely new substrates such as quantum computing structures that can operate at minimal energy levels. Communication and travel will present significant challenges in a degenerate universe, possibly forcing surviving beings to develop highly advanced forms of information storage and transmission capable of surviving the long cosmic night. Information may become the primary currency of exchange, and the preservation and transfer of knowledge will be vital to the preservation of any form of society. In a universe heading towards its ultimate fate, be it heat death, the Big Rip, or some other scenario, our understanding of time and causality, the fundamental concepts underlying our perception of reality, may be profoundly tested and altered. The arrow of time, a metaphorical expression used to describe the one-way direction or asymmetry of time, is closely related to the second law of thermodynamics, which states that entropy in a closed system does not decrease with time. As the universe evolves toward a state of maximum entropy, nuances may emerge in the very fabric of time and causality that are not accounted for in our current understanding. In the distant future, as the universe approaches a state of thermal equilibrium in a heat-death scenario, the absence of discernible events may make it appear from some vantage point that the flow of time has stopped. Without changes in the energy states that mark the passage of time, beings in such a universe would not be able to experience time in any meaningful way. This raises philosophical questions about the nature of time. Is it a fundamental part of the universe, or is this an emergent property, dependent on the existence of change and causality? The concept of causality, the relationship between cause and effect, may also be reconsidered in a universe nearing its end. Quantum mechanics is already challenging classical notions of causality with phenomena such as entanglement, where particles can affect each other instantaneously regardless of distance, seemingly contradicting the conventional flow of time. As we explore the fate of the universe, we may find that the fabric of space-time and the rules governing causality on cosmological scales create new paradoxes and possibilities that are beyond our current quantum mechanical understanding. Moreover, if speculative theories such as the cyclic model of the universe, in which the universe undergoes an endless series of expansions and contractions, or the existence of a multiverse, prove true, our perception of time as a linear progression from a singular beginning to a singular end may be too simplistic. In such scenarios, time may be better conceptualized as a more complex, perhaps even multidimensional landscape where causality operates in ways that are not immediately intuitive to our current thinking. These considerations suggest that, as the universe evolves, the beings living in it, if only they can survive the harsh conditions of the distant future, may develop an entirely new framework for understanding and perceiving time and causality. These frameworks may account for the altered physical conditions of a maximally entropic universe, or incorporate insights from quantum mechanics and theoretical physics that challenge our current paradigms. Quantum fluctuations, temporary energy changes occurring in a seemingly empty vacuum, represent the cornerstone of quantum mechanics, revealing the inherent unpredictability and activity of the quantum vacuum. In the context of a dead universe, a space near or reaching maximum entropy, devoid of stars and galaxies and approaching absolute cold, such fluctuations could still occur. Intriguingly, some theoretical physicists suggest that, under the right conditions, quantum fluctuations can give rise to new universes, suggesting that cosmic events may be cyclical. In a universe that has reached its final state, where matter is dilute and energy is evenly distributed, the fabric of space-time can still experience quantum fluctuations. In principle, these fluctuations could lead to the formation of low-energy virtual particles, a phenomenon observed in the laboratory. Extending this concept, it suggests that under extremely rare and specific conditions, a quantum fluctuation can create a localized concentration of energy dense enough to cause a new Big Bang, generating a new universe within the old one. This concept is related to the idea of a multiverse, where our universe is just one of potentially many universes, each with its own physical laws and constants generated by the quantum foam of a larger multiverse. Such a process implies cyclicity, or at least a constant nature of cosmic events, where the death of one universe sets the stage for the birth of another. The implications of such a scenario are profound, challenging our understanding of time, causality, and the very nature of existence. If quantum fluctuations can indeed produce new universes, this suggests that the cosmos is eternally rejuvenated, with cycles of birth, evolution, and death followed by rebirth. This cyclic model contrasts with the linear progression from Big Bang to heat death traditionally represented in cosmology. Singularities inside black holes, points of infinite density, where the laws of physics as we know them break down, have long fascinated physicists and cosmologists. A tantalizing hypothesis suggests that these singularities may not simply mark the end of the journey of matter within our universe, but may also serve as seeds for the birth of new universes. This idea suggests a profound connection between the end of one cosmic epoch and the beginning of another, weaving a tapestry of universe creation that links the life cycle of black holes to the genesis of entirely new cosmoses. At the heart of a black hole, matter collapses into a point of infinite density and zero volume, forming what is known as a singularity. The conditions in these singularities go beyond our current understanding of physics, potentially involving the unification of general relativity theory, which describes gravity at cosmic scales, and quantum mechanics, which explains the behavior of particles at the smallest scales. Some theories, such as the concept of quantum gravity, attempt to describe these conditions by suggesting that the extreme gravity of a singularity can tear the very fabric of space-time. Theoretically, this rupture could create a bridge or wormhole to another region of space-time, giving birth to a new universe that expands in its own dimension separate from our own. The new universe does not necessarily inherit the physical laws or constants of its parent universe, allowing for the creation of a variety of cosmoses with very different properties and complexity potential. The implications of black holes serving as seeds for new universes are profound. This challenges our understanding of causality, as the birth of a new universe from a black hole singularity means that the end of one world is inextricably linked to the beginning of another. This cyclic process could provide a mechanism for the emergence of a multiverse, where each black hole in our universe is capable of generating a new universe, leading to an ever-growing ensemble of universes. This concept changes our view of black holes from cosmic endpoints to gateways of cosmic rebirth. This suggests that within each black hole lies not just the end of certain paths in space-time, but the potential for entirely new beginnings. This view is consistent with the broader view of modern cosmology that the universe is a dynamic, constantly evolving entity, with processes at both the largest and smallest scales that contribute to the cosmic life cycle. If the multiverse theory is correct and suggests the existence of multiple universes beyond our own, each with potentially different physical laws and constants, this opens up profound questions about the nature of consciousness, information, and their persistence beyond the life of a single universe. The intriguing possibility that consciousness or information could leave a dying universe and find refuge in another universe touches on the intersections of cosmology, quantum mechanics, and theories of mind and information. The basis of this speculative journey lies in understanding the mechanisms by which such a transference can occur. One theoretical path is related to quantum entanglement, a phenomenon where particles appear to be interconnected in such a way that the state of one of them, regardless of the distance between them, instantaneously affects the state of the other. Extending this concept, some theorists suggest that if every bit of information in our universe, including the states that constitute consciousness, could be entangled with particles in another universe, then, in principle, information transfer would not be associated with the death of the parent universe. Another potential mechanism is black hole singularities, which it is thought could serve as bridges or wormholes to other universes within the multiverse. If consciousness or information can be encoded in a form that survives a journey through such a singularity, it could be another avenue of escape from a universe facing doom. For consciousness itself to make such a leap, it is necessary to radically expand our understanding of consciousness as not just a product of brain activity, but as something that can exist independently of a biological substrate. This concept relies heavily on the realm of digital consciousness or mind uploading, where human consciousness can be replicated on a non-biological platform capable of surviving the extreme conditions of inter-universe travel. However, each of these speculative paths faces serious scientific and philosophical obstacles. Quantum entanglement, although experimentally confirmed, currently makes it impossible to transmit information in a way that encompasses consciousness. Similarly, the nature of singularities and wormholes, and their ability to connect to other universes, remains purely theoretical and limited to our limited understanding of quantum gravity. The transference concept of consciousness suggests that it can be fully understood and reproduced outside of its biological context, and this claim raises profound questions about the nature of identity, selfhood, and the continuity of experience. As the universe approaches its ultimate fate, the principles of quantum mechanics and information preservation play a key role in shaping theories about the final moments of the universe and the possibility of its eventual rebirth. Information retention. A principle deeply embedded in quantum theory states that information, defined in the broadest sense encompassing all possible states of a system, cannot be destroyed even if it can be transformed. This principle has profound implications for the ultimate purpose of the universe and the concept of cyclicity or rebirth in cosmological models. At the center of these discussions is the concept of the black hole information paradox, which asks, what happens to information trapped in a black hole? Stephen Hawking's discovery that black holes emit radiation, Hawking radiation, and can eventually vaporize, has challenged the idea that information trapped in a black hole is lost forever. If black holes vaporize without leaving a trace, the question arises, where does information go? The principle of conservation of information suggests that it must be stored in some form, perhaps encoded in Hawking radiation itself. This debate has prompted more research into the nature of information at the quantum level and its implications for the universe. One theory suggests that at the end of the universe, all of its information could be encoded on a two-dimensional surface at its boundary, adhering to the holographic principle, which suggests that the entire volume of space can be described by the information at its boundary. This model could mean that, as the universe approaches its demise, all information about its history, structure, and content, perhaps even the rudiments of consciousness or life, could be preserved at this cosmic boundary. Theoretically, this stored information could be the basis for the rebirth or regeneration of the cosmos. If the universe is cyclic, as in models involving a series of big bangs and big compressions, then the information preserved at the end of one cosmic cycle could affect the initial conditions of the next. In such a scenario, the rebirth of the universe would not be tabula rasa, but would bear the imprints or echoes of its previous incarnation, guided by the fundamental laws of quantum mechanics and conservation of information. Progress in understanding quantum gravity, a theory that seeks to reconcile general relativity with quantum mechanics, may reveal the mechanisms by which the information preserved at the death of the universe affects the very fabric of space-time, potentially laying down the geometry and distribution of matter of the new universe. It is a symbol of a world where ends and beginnings connect, care for each other, and protect information. Human understanding and reflection on the end of life offers profound lessons about our place in the world and our approach to life issues, and provides us with a humbling and inspiring perspective. When we look at the vastness of the universe and think of its future, we are reminded of our smallest scale in space and time. Of course, this does not diminish our intelligence. Instead, it increases our appreciation of the complexity and beauty of the world and our ability to understand it. The cosmic perspective teaches us about the transience of existence, not only on a personal or species level, but on the scale of stars, galaxies, and the universe itself. It instills in us a sense of cosmic humility, recognizing that we are part of a much larger and ancient process far beyond our immediate concerns and lifespan. Realizing this can shift our existential questions from a human-centered narrative to a broader and more inclusive understanding of our place in the cosmic web of life and matter. Moreover, thinking about the end of the universe and the principles that govern it, such as entropy, the conservation of information, and the possibility of cyclic universes, causes us to think deeply about the nature of time, causality, and existence itself. These concepts expand the boundaries of human thinking, inviting us to consider that our universe may be one of many, that our existence is part of a larger cosmic cycle, and that the legacy of humanity and life as we know it may be encoded in the very fabric of the cosmos. Exploring these ideas also has practical implications for how we relate to our lives and stewardship of our planet. Recognizing the rarity and value of life in the context of the cosmos can inspire a deeper sense of responsibility to preserve and cherish the delicate conditions that allow life to thrive on Earth. This can motivate us to strive for a sustainable existence, to explore interstellar space, and to preserve knowledge, culture, and biodiversity for future generations. The realization of the ultimate end of the universe provides a powerful stimulus for human creativity, philosophical reflection, and the urgent need to find meaning in our existence. This profound realization that the cosmos itself is not eternal and unchanging, but subject to decay and transformation, touches the very core of our understanding of life, purpose, and the nature of existence. It forces us to face the finitude of everything we know and challenges us to find meaning and purpose within those boundaries. In terms of creativity, thinking about the demise of the universe has inspired countless works of art, literature, and music, as well as innovations in science and technology. Artists and thinkers have long addressed the themes of impermanence and the end of time, using these concepts as a backdrop against which the drama of life unfolds. The vastness and mystery of the cosmos, coupled with its ultimate end, serves as a muse for exploring the depths of human emotion, fortitude, and boundless capacity for imagination. This realization motivates scientists and innovators to go beyond our current capabilities, to explore the cosmos, to comprehend the fundamental laws of nature, and to contemplate the possibility that we may go beyond our earthly origins and perhaps even the lifespan of our universe. Philosophically, the end of the universe forces us to reconsider the existential questions and values that guide our lives. It prompts reflection on the nature of values, ethics, and our responsibilities to ourselves, to each other, and to the continuity of consciousness and culture. The finitude of the cosmos can lead to a deeper appreciation of the moment, a deeper investment in the legacy we leave behind, and a deeper understanding of the interconnectedness of all things. Such a perspective fosters a philosophy of stewardship that emphasizes the nurturing of life, knowledge, and beauty, despite, or perhaps because of, their transitory nature. The need to find meaning in our existence is perhaps the most direct consequence of thinking about the end of the universe. Faced with the ultimate impermanence of all things, people begin to seek purpose in their actions and relationships, to create and share the beautiful, and to make a lasting impact on the world and those around them. This awareness can lead us to move from seeking external validation to cultivating inner wealth, from accumulating material goods to enriching the world with contributions that can endure through time. In envisioning the preservation of knowledge through the ages, humanity stands on the threshold of an endeavor that strikes the imagination to the extreme. This mission to pass on the legacy of our knowledge and existence to possible future civilizations or minds requires innovative methods and messages that can withstand the ravages of time and the uncertainty of cosmic events. The challenge is not only to preserve information, but also to make it understandable to people with potentially very different perceptions, languages, and technological capabilities. One approach to this grand challenge is to create lasting time capsules or monuments that are designed to last for millions or even billions of years. These could be plaques or sculptures made of materials resistant to erosion, corrosion, and cosmic radiation, such as platinum or silicon carbide. One example is the Voyager Golden Record, which is currently traversing space aboard the Voyager spacecraft, and contains sounds, music, and images selected to represent the diversity of life and culture on Earth. Another method involves encoding knowledge in the structure of DNA, taking advantage of its longevity and compactness as a storage medium. Scientists have already made advances in storing digital data in DNA, a technique that could be extended to archiving vast amounts of information about human history, culture, science, and technology. DNA can be encapsulated and placed in many places on Earth and beyond in the hope that future beings, whether descendants of humanity or extraterrestrial intelligent beings, will be able to decipher it. The messages we choose to preserve should be composed with universal principles and concepts in mind, aiming at a level of communication that transcends human language and cultural sensitivities. These could be mathematical sequences, physical constants, or simple pictograms depicting fundamental aspects of human anatomy, the location of the Earth relative to known celestial objects, and basic concepts of chemistry and biology. An example of this approach is the Arecibo message sent into space in 1974. It used binary code to transmit basic information about humanity and the solar system. In addition to physical methods, humanity might consider more speculative strategies, such as attempting to transmit information through time using quantum entanglement or other phenomena that lie beyond our understanding of physics. Although such ideas belong to the realm of science fiction, they reflect the breadth of creative thinking aimed at solving the problem of intertemporal communication. In addition, a method of preserving knowledge can be the development of a culture of preservation and continuity within human civilization itself. This could include the continual updating and preservation of knowledge repositories, specialized institutes, or digital archives designed to survive global catastrophes and be accessible to future generations. Such repositories would hold not only information, but also instructions for interpreting the data, perhaps the keys to understanding human languages and technology. As humanity becomes more aware of the universe and our place in it, the realization of our ultimate destiny brings to the fore a number of ethical considerations of cosmic proportions. These considerations challenge us to think about how we interact with the cosmos, what responsibility we have to future generations, and how we should interact with potential extraterrestrial life. Our actions, motivated by the realization of the immensity of the universe and its ultimate demise, have implications that go far beyond our immediate concerns and go to the very core of our heritage and stewardship of the cosmic environment. First, ethical engagement with the universe requires a deep respect for the cosmos as the broader context of our existence. This respect is manifested in the desire to preserve outer space and to refrain from activities that could have a negative impact on the celestial environment. As we venture into space, the principles of non-pollution and preservation of celestial bodies in their natural state become paramount. These principles not only preserve the scientific integrity of these environments for future exploration, but also consider the intrinsic value of the cosmos beyond human utility. Second, our understanding of the fate of the universe increases our responsibility to future generations. This responsibility entails ensuring that future generations inherit a wealth of knowledge and a culture of curiosity and exploration. It also involves developing and preserving technologies and information that can help humanity meet the challenges of a changing universe, including the search for new habitats beyond Earth. The need to invest in long-term sustainable life and interstellar exploration is a testament to our commitment to the continued existence of humanity and Earth. Furthermore, the prospect of encountering extraterrestrial life raises complex ethical dilemmas concerning communication, coexistence, and knowledge sharing. The principles of mutual respect, non-interference, and the peaceful exchange of resources and information must underpin our interactions. Recognizing the rights and autonomy of other living beings and interacting with them in ways that promote mutual understanding and respect represents our commitment to ethical behavior not only at home, but also in space. We travel into space to make discoveries and look beyond reality itself. What if the cosmos is invisible in all its glory? Could it be that our universe is an illusion, a complex facade covered by the complex laws of physics? Our quest leads us into a labyrinth of time, moving endlessly through the universe. Time stretches, compresses, and binds all aspects of existence. It acts as an invisible link, connecting the past, the present, and the uncertain future, forming the foundation of our reality. As our journey reaches its climax, we will encounter two formidable pillars of understanding: the speed of light and the mysterious force of gravity. The speed of light, the boundary that separates the possible from the impossible, and gravity, the invisible force that represents the interaction between all matter, bending the fabric of space and time. Through them, we will try to decipher the cosmic code that governs the universe. Fasten your seatbelts for an unknown space journey, where we challenge our understanding of the universe based on the principles of time, light, and gravity. Everything around us, even ourselves, is part of our universe. We are used to thinking of it as something ephemeral. But what is the universe? Today, we're going to challenge what you know about the universe. What if everything we see and feel is an illusion? Hold on, because we're about to delve into the mysteries of the universe. First, let's look at what we know about the universe. For scientists, the paradox of how our universe was formed is still a mystery. As we know, 13.8 billion years ago, according to the Big Bang theory, the universe was formed from a singularity where all the fundamental forces converged. On the other hand, according to the Hawking-Hartle theory, the universe did not originate from a single point. It existed as pure space without time, with the Big Bang coming later. Despite the diversity of current ideas about the origin of the universe, cosmic inflation began at some point. Protons and neutrons formed in microseconds, forming basic building blocks like hydrogen and helium. Then, after cooling, 360,000 years later, light, and millions of years later, stars and galaxies. As a result of the expansion caused by the Big Bang, we can see other galaxies moving at high speeds. And so, 1 billion years after the Big Bang, the universe as we see it came into existence. But what do we mean when we talk about the observable universe? The part of the universe that we can see may not be very large. It's actually about 93 billion light-years. What each of us sees is the matter and energy that fills space. Surprisingly, the fraction of ordinary matter that makes up stars and planets is tiny compared to the hypothetical dark matter we have yet to detect. However, the most interesting thing we know about the universe is life. According to the principles of physicist Brandon Carter, we exist as observers, and the universe conforms to our existence. And the universe must be like observers. That is, the universe can be such that our existence is possible. This leads to the fundamental question: does the universe exist apart from us? Let's turn to quantum theory. Physicist John Wheeler, colleague of Albert Einstein, modern observations suggest that they can influence the behavior of photons. A famous experiment with photons directed at two pieces, and a screen shows that observers with detectors can influence the behavior of photons. Thus, if there are observers, the photons act like particles and pass through one of the two slits. However, without observers, the photons behave like waves and pass through two slits at once. Wheeler decided to take the experiment to the cosmic plane, pointing the photon gun at the quasar and moving the slits to two nearby galaxies. Thus, the photon may have started billions of years ago, before life and the development of photon detectors, forced to go to those detectors. That is, the motion of light always depends on the observer. Does this mean that the universe cannot exist without humans? Not really. It is true that humans are capable of receiving information, analyzing it, and reproducing it for others. But they are not the only watchers, even if they are perfect. Following Wheeler's model, high-energy particles, which can exist in different states, can interact with rocks on Earth. Thus, the stones will leave a trail of particles, which means that new information has been exchanged. Therefore, according to this hypothesis, the universe does not need consciousness. Another experiment in quantum mechanics confirms this. 3 scientists who recently shared the Nobel Prize, John Clauser, Alain Aspect, and Anton Zeilinger, were able to prove that the universe is not local. This, of course, does not mean that the universe as we know it does not exist. Physics distinguishes between the principles of reality and locality. Reality means that an object exists and does not change its properties even if no one observes it. A red apple will remain with or without measurements. Area, in turn, is explained by the fact that objects can be affected only when they are related to each other, and these distant bodies cannot interact with each other, for example, at the speed of light. If you send a light signal to a friend 10 light years away, you won't get a response after turning on the flashlight. This leads to the principle of local realism or the principle of hidden variables, according to which objects with certain characteristics exist at some intangible level and are independent of observations. In other words, we live in an objective reality with a certain set of factors, independent of our consciousness. But physicist John Stuart Bell disagreed. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper under the acronym EPR, in which the theorists attempted to prove the absurdity of quantum physics. They questioned the possibility of quantum communication. If two particles are bound, they are conserved even if they are in different parts of the universe. For example, if a particle rotates clockwise, other particles associated with it rotate counterclockwise. So, if one piece is on Earth and the other piece is 1,000 light-years away, then, knowing the direction or rotation of one of them, one can immediately know in which direction the other is rotating. This contradicts GR because nothing can travel faster than light. So, 30 years after EPR was published, Bell conducted a thought experiment. He continued with the EPR idea, but refined it a bit. He envisioned two observers, Alice and Bob, in different parts of the solar system and with particle detectors, but with two different settings, A, B, B, for more precise observations. Thus, if the local theory of reality were true, one particle would have no way of knowing what parameters another has. Results are always random. If quantum theory is correct, then the particles would be perfectly correlated. 3 Nobel laureates, Clauser, Aspect, and Zellinger, were able to replicate the experiment in reality. By counting the number of times Bob and Alice agreed with each other about the state of the particles, they confirmed Bell's theorem, proving that the universe is not locally real, meaning that everything in the universe needs an observer. That's why we can breathe. The universe exists as we think it does. However, what if I told you that this might not be the case and that our brains are deceiving us? From our perspective, according to Einstein's GR, the universe is a continuum of space-time with 3 dimensions and 1 temporal dimension. All massive objects in our universe, including our Earth, can cause gravity to dissipate time. Yes, we monitor all of this. What could be cheating? Perhaps our 4-dimensional universe is a holographic projection. It sounds fantastic, but this theory is being seriously considered by scientists. Everyone has probably seen a hologram, a deep 3-dimensional image created on a flat surface using light. The light produced by the holograms contains a large amount of encoded information. For example, texture or relative distance. Thus, from all angles, the image will appear 3-dimensional. Theoretical physicist Juan Maldacena suggests that our universe might be like this. Everything you see in 3 dimensions is in 2 dimensions. Black holes helped develop this idea. Black holes can increase their mass at the expense of other objects falling onto them. But these objects do not disappear. They remain in the black hole. But black holes can decay. Renowned physicist Stephen Hawking discovered that black holes evaporate and then disappear completely. What happens to data that falls into a black hole? Will it be gone forever? This goes against the basic laws of physics because matter cannot disappear. They change to another state according to the principle of conservation of mass. However, the idea of the holographic nature of the universe can solve this paradox. The holographic theory is explained through the hypothetical doubling of two other mathematically equivalent theories, the ADS-CFT correspondence. Anti-de Sitter space, ADS, a space closely related to negative space and constant theory, has a curved parabolic shape in more dimensions than required by line theory. This space is often defined as 5 dimensions, but it can have up to 10 dimensions. ADS also has limitations, unlike the popular model of the universe. Modern cosmology suggests a flat universe model, similar to a simple universe, where 2 lines or 2 light waves will always be parallel. If the universe is truly perfect, it may not have boundaries, but it's possible that our universe is so warped in unimaginable disintegration that satellites can't see it. Therefore, the UDS can be thought of as a 3-dimensional ball with a finite surface, but it is very flat. This theoretical limit is crucial for the second theory in this theory, conformal field theory. CFT describes the behavior of particles and fields in flat space and is one-dimensional compared to ADS and has no particular gravity. So there is a dualism that allows us to look at the system from 2 sides. Internally, what is in ADS can be translated to CFT and vice versa. So their duality is like a borderline hologram, encoding everything inside. Thus, according to ADS-CFT, information entering a black hole does not disappear without a trace. Information can be encoded in the 2-dimensional event horizon of a black hole, beyond which the gravitational disturbance is so strong that even photons cannot escape. Thus, the data is not lost, only moved up. This duality theory does a good job of explaining these and other modern mysteries of the universe, but it has several problems. For example, the ADS-CFT correspondence works in a negative spatial constant universe model. However, according to current observations, our universe has a positive constant value and is still expanding. So, we probably don't live in a finite universe. For example, in 1929, astronomer Edwin Hubble concluded that the universe was continuing to expand and that this process could continue forever. Therefore, since our observations are limited, the question of the infinity of the universe remains open. This point is crucial to the whole theory. So now the idea of ADS-CFT has mathematical value. But if we can find answers to all the findings of the theory, we can prove that the universe is a hologram. The question of what our universe is worries not only physicists, but also philosophers. In 2003, philosopher Nick Bostrom suggested that some scientists, such as Elon Musk, think it's somewhat possible. What if we are living in a simulation? In his paper, Bostrom argues that one claim about simulation capability must be true. First, humans will die before they reach a technological level that would allow them to create the most complex simulations. Second, it is highly unlikely that an advanced civilization would be interested in imitating its history. 3 advanced civilizations are creating simulations, and we live in one of them. So, if the third idea is true, we could live in a completely simulated world like computer games. Of course, this hypothesis cannot be tested empirically, but we may have some evidence to support the simulation hypothesis. About the speed of light. According to Einstein's theory, we know very well that the speed of light is limited to 186,000 miles per hour. Therefore, all the light we see from the stars takes a long time to reach us. A simulated device cannot have unlimited computing power. There must be some limits, and it's these limiting artifacts that we can observe at the limit of the speed of light. So, if this hypothetical computer processor running the simulation could perform 1 operation per second, it will have a warranty of 186,000 miles. In particular, the simulation can also explain the principles of quantum mechanics. As with subatomic particles, we define their state by looking at them. Thus, based on the simulation hypothesis, We see only the indicated part of the universe graph, and the rest of the graphs remain empty. And yet, despite the interesting explanation, by limiting the speed of light, a simulated universe is considered a speculative hypothesis because it cannot be proven or disproved. Maybe someday, if this hypothetical computer matrix starts to fail, we'll reconsider this idea. So, the universe is still a great mystery to us. We cannot believe that everything we see is not an illusion. As we have said, we are aliens to the universe, but what if we should never live? The Earth, the Sun, and our galaxy were never meant to be. CERN scientists believe that symmetric matter and antimatter must have been created after the Big Bang. So, if this scenario were to happen, all the particles had to come together to destroy the whole. However, something has created an imbalance between the two substances, and it is not yet known what it is. So we can say we are happy because we are here now, and we would be able to observe the universe and discover all its secrets. Do you think that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the force that governs our existence and seems to dictate the rhythm of our lives, is not what it seems. For example, time seems to slow down for objects traveling near the speed of light, and it flows at different speeds depending on the force and gravity around us. Have you ever considered that time may be a figment of our imagination, a construct our brains come up with to make sense of the world? In search of the truth behind this mysterious concept, you will have to step into the unknown and question everything you know about time. Time, in its simplest form, is a tool we use to measure change and organize the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles, like day and night, or the changing of the seasons. It was important in coordinating activities such as farming, navigation, and religious rituals. Early methods of telling time were based on natural phenomena, such as sunrise and sunset, the phases of the moon, and the positions of the stars. As human society has become more complex, so have our ways of measuring time. To divide the day into smaller and more manageable parts, we developed instruments such as sundials, water clocks, and finally, mechanical clocks. Calendars are designed to track the passage of long periods of time, such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of people's understanding and interpretation of time. Although timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brain processes and interprets time differently, depending on factors such as age, emotional state, and cultural background. This suggests that time is not a fixed universal phenomenon, but a flexible construct shaped by our experiences and needs. Despite the presence of time in our lives, it remains a somewhat illusory concept. This begs the question, is time an objective reality, or is it a construct created to bring order to our chaos? So, let's look a little deeper into the history. The traditional understanding of time as an independent, constant entity was challenged by Albert Einstein's groundbreaking work in the early 20th century. Einstein's theory of relativity introduced the concept of time as a measurement, forever changing the way we think about this mysterious phenomenon. Einstein's theory of relativity arose from the nature of light and the concept of absolute space and time that was central to classical physics. He argued that the laws of physics must be the same for all observers, regardless of their relative motion. This revolutionary idea led to the development of two related theories, special relativity and general relativity. In his theory of special relativity, Einstein showed that space and time are not separate entities, but are bound together in a single continent called space-time. In this four-dimensional frame, time is transformed into a fourth dimension, and events are represented as points in space-time. This concept overturned the traditional view of time as an independent variable, showing that it is an integral part of the structure of the universe. Einstein's theories also showed that time is relative and depends on the reference of the observer. According to the theory of special relativity, two events that appear to one observer at the same time may appear to move relative to the first to a second observer at different times. This phenomenon, also known as relative relativity, makes it difficult for us to perceive time as an absolute and constant unit. General relativity extended the ideas of special relativity and brought gravity into the picture. According to this theory, large objects such as planets and stars cause periodic distortions, and this vein is captured by the force of motion in it. The presence of a large object can also affect the passage of time, resulting in a phenomenon known as gravitational time dilation. According to the theory of special relativity, time dilation occurs when two objects are moving at relatively high speeds relative to each other. If an object is moving faster, time passes more slowly compared to a stationary observer. This effect becomes apparent when approaching the speed of light. This phenomenon is best illustrated by the famous twin paradox. In this case, one twin travels close to the speed of light, while the other twin remains on Earth. Upon return, the traveling twin will be younger than the earthly twin due to the time difference. In general relativity, time dilation is also caused by gravity. Time moves more slowly in stronger gravitational fields, such as near large celestial bodies such as planets or stars. This effect was tested experimentally using atomic clocks located at different altitudes. Clocks closer to the Earth's surface run slower than clocks at higher altitudes where gravity is stronger and gravity is weaker. Time dilation, although seemingly illogical, has been experimentally verified and has practical applications. The best example is the Global Positioning System, or GPS. Earth-orbiting GPS satellites experience time dilation due to acceleration and gravity, which must maintain accurate time and location. Furthermore, gas pedal experiments for high-velocity particles have confirmed that particles traveling at the speed of light experience significant time dilation, as predicted by the theory of special relativity. Before Einstein's theory of relativity, time was considered the unchanging and universal background for all events in the universe. Isaac Newton, for example, believed in the concept of absolute time, which is uniform and flows independently of the events it measures. However, discoveries related to time expansion. The theories of special and general relativity refute this notion with the relative nature of time, and prove that time is not a constant but a variable quantity depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also implies a strict adherence to casuistry, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events can depend on the reference of the observer, which can lead to cases where cause and effect appear to be reversed or simultaneous. This complicates our intuitive understanding of randomness and forces us to rethink our ideas about the way things work in the universe. The concept of the arrow of time, the idea that time flows in one direction, from the past to the future, based on our understanding of the world, has also been questioned. However, relativity's relativistic nature of time and random reversals force us to reconsider whether the arrow of time is a fundamental aspect of the universe or a construct of human perception. As the traditional view of time as an absolute entity was undermined by the discoveries of relativity theory, some scientists and philosophers suggested that time might be an emergent property rather than a fundamental aspect of the universe. From this point of view, time arises from the connection and interaction between objects and events, rather than being independent of them. Leaving aside the problems of Einstein's theory of relativity, we move into the more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and ambiguous, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic level. It is governed by a set of probability rules that differ from those of classical physics. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition, and their properties can only be determined by measurement or observation. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics describes time as a continuous and absolute unit, quantum mechanics treats it as a discrete numerical parameter. This time leads to situations that lose their traditional meaning and play an abstract role. For example, consider the following everyday scenario. You watch wild animals and see how they behave differently when they know they are being watched. As you get closer to them, their behavior changes, and it becomes difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also known as Heisenberg's uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can perturb the state of a quantum object, such as an electron. Just as your attempt to observe wild animals affects their behavior, observing or measuring a quantum object can affect its position or momentum. Heisenberg's uncertainty principle states that the position and velocity of a quantum object can be known simultaneously with absolute precision. The more accurately we measure one property, the more accurately we can know the other. In the quantum world, the act of observation or measurement can collapse the wave function of a particle and move it from a superposition of multiple states to a specific state. This process is inherently problematic, and the outcome cannot be predicted with certainty. Considering the phenomena of quantum superposition and the observer effect, it becomes clear that our traditional understanding of time as a linear progression may not be correct at the quantum level. Instead, the quantum world offers a more fluid, interconnected vision, where the boundaries between past, present, and future are not as rigid as we think. As we have seen, our understanding of time is closely related to our understanding of space. This complex relationship has given rise to many theories that attempt to explain the nature of space,